Circular motion problem for number 21, just continuing on our answers to the multiple choice smorgasbord I've made available to you. So this is one of the most important problems where you have an object moving around in a circle. So when the string snaps, just to be clear, the object always leaves tangent to the circle. So path 3 is always the right choice on these problems. It's just a fundamental fact that it's always good to know. Here. Spacecraft separation. This is a classic conservation of momentum problem. So let's get the total momentum before. This is going to be 3mv. Why? Because this is 2mv plus mv. Now here, after the separation, we get 2m at its velocity of 0 plus m at its v final. And what we can do is we can set these equal. And when we do that, what we're going to end up getting is at v final ends up being 3 times v, which is choice C. Now for number 23, this is the classic kind of trick question. We've got 2 paths to get to Q, and we've got energy conserved. So just to be clear, the trick for these problems, and I think this one actually repeats, so let me just give you the trick. The trick is this. Path doesn't matter. Only change in height for the final speed. Now, there may be different times associated with the trip, but as far as speed goes, whether we take path 1 to get to Q or path 2, the speed will be the same. So that's question number 23. And then continuing with question number 24, let's just kind of be clear. Let's get a few kind of things established here. Whenever you see the word field, any kind of field in physics, gravitational field, electric field, we'll encounter those in next year, but when you read this word field, just know that that's a vector quantity. And let's just distinguish one more time, just to be clear. Remember, a scalar just means a number, and a vector is a number with a direction. They will say it has magnitude and direction, just like that villain from, Despicable Me. Okay. So, scalar quantity, acceleration is a vector, momentum is a vector, electric field is a vector. Only power is a scalar. Now we have a motor car. I don't know why they say that. All right, a motor car travels on a circular track of radius A as shown. So we're going from P to Q. So let's remember the displacement means the distance from your beginning point to your ending point in a straight line. So look what we have here. We actually have the hypotenuse of a triangle. So this is A, and this length here is A radical 2. So that actually rules out C and D as choices. But we started at P and we went to Q. So our direction was in the western direction, going south. So that's choice A. So to be clear, just to review, if this is a path, okay, and this is A and this is B, okay, distance, you know what, let me just draw this a little bit more obnoxiously. Okay, if this is A and this is B, okay, distance is the length of this road. Displacement is this straight line distance connecting A with B, like that. So that there is the displacement. Just to be clear. So if we traveled around this circle and we asked you for the distance from P to Q, that would be 2 pi r divided by 4. And in fact, let me write that in the right color. The distance, in this case, would be 2 pi r, the whole circumference, but 1/4 of that. So that ends up being pi over 2r is the distance. To be clear, displacement is a vector. It has direction. Distance is a scalar. All right. 26. The fish swims with constant velocity. That means the net force is 0. That comes up so many times in IB. Okay, so I hope this one's getting a little stale at this point. We're going to find out that as I continue in these videos, you'll notice the time to do 10 questions is going to get shorter and shorter as you notice certain concepts kind of repeating themselves. Now, we got a stone falling towards Earth. Once again, a repeat question. The force that the stone exerts on the Earth is exactly equal to the force that the Earth exerts on the stone. This, once again, is Newton's third law. I want to type it out one more time just to be clear. It says if A pushes B, or if A pushes or pulls B, B pushes or pulls back on A with equal and opposite force. Okay. I don't like saying for every action there's an equal and opposite reaction, because people start thinking about like some kind of weird karma stuff, you know, like if you put good in the universe, good comes back. We're much more specific than that. Please think of it in terms of forces, that if I push you, you're going to push me back with equal and opposite force. Or rather, if any object pushes another, there's an equal and opposite force going the other way. Now, here, we've got this force, and we want to know what the value of this force. So let's be clear. This is the tension right here. Let's just be clear on how this works. So the tension force has two parts. There is here when we do our trig. Okay. So the angle that matters, let's just be clear on this. I'm going to rewrite the tension here. Now here's the angle theta. For our components, okay, I have one component that goes this way. If we're going to use SOHCAHTOA, look carefully at this. This component here is t sine theta. This component here is t cosine theta. So we've got a, t cosine theta component here. So if we want to know what component balances F to keep it still in the horizontal direction, it's just C. Sorry, not cosine. I apologize. It's t sine theta. So there's our correct choice. Now, question 29. Okay. Object suspended by a string rotates with constant speed in a horizontal circle. Okay, so the object is not in equilibrium. Let's be absolutely clear. So constant speed is not equilibrium if you move in a circle. Okay, I want to be really clear on that. That's such an important point. Okay, that I cannot emphasize enough. It's such an important point, I'm going to write it in bold. The force acts in the direction of motion. No, in fact, since we're moving at a constant speed in a circle, the net force is actually directed towards the center of the circle. Again, it's the same idea coming up again and again, that when you move in a circle at a steady speed, the net force is directed towards the center. Then for number 30. Okay, so we've got two vehicles moving towards each other. Let's actually just sketch it out. So we've got A and we got B. And they're moving towards each other, which is cool. So we've got 1,000 moving at 5. And we got 500 moving at -20. Again, going backwards. That's why I put the negative there. So I'm going to actually write -20 because it's going backwards. We know it's going backwards because they're moving towards each other. So I've got 5,000 minus 10,000, and we want the total momentum. So I'm getting -5,000 kilograms meters per second. But they want the magnitude. Magnitude is another term for size or absolute value. So that's how I'm getting 5,000. All right, so that's question number 30, and we will continue doing 31 through 40 in the next set of videos.